Okay, here's where we want to launch our day today. Yesterday we went through some translations. It's really important that we're able to translate between exponential and logarithmic format. Okay, so that's one skill that you have to be able to show me on your assessment. Show me that you can take an exponential expression and convert it into log format. Start with a log format and convert it to an exponential. That means you have to be able to take these three building blocks, the base, the exponent, and the antilog, and put them in the corresponding spots for a logarithm. There's some other ideas here that you've got to get into your mind. That when you hear the word logarithm, it's really synonymous with exponent. You've got to start relating. Logarithms are really nothing more than another way of saying exponents. Logarithms basically always find exponents. Since they're always finding exponents, logarithms are the inverse operation of exponentials. The bottom line is we had to introduce a new operation to you so that you could finish PEMDAS backwards. We're at the end of the year, your junior, sophomore years, and we're to the final stages of putting in place how we undo exponents, and that's with logarithms. So at the end of the day, we studied inverse operations so that we could bring in another inverse operation of exponents. We're going to use these to solve equations. Okay, so we've got to kind of push now a little bit. I need you to be cooperative, I need you to be engaged, I need you to write things down, I need you to go quickly. Here's some practice right away. I want you to change that from a log format into an exponential format, and I want you to commit it to paper so that you have to commit something. Not just log it around in your mind and let it roll around in there. Jot it down. Right there. We're going to do several of them, so you might want to just take a paper out and put it somewhere.
It's in there.
But you're not done. There's still more to the story.
Oh.
Okay, let's see if we're on track. With this skill, what I'm looking for, number one, if there isn't a base written, what is always the base if there's nothing written? So our base of our exponent must be 10, and since logarithms always equal exponents, that has to be the exponent. Here's my antilog, 001. Another one. You don't have to. If you did, what would x have been? Excellent. Nice job. That would have been negative.
Negative 3. Negative 3. You don't know anything, and you're throwing me out. That's throwing me out. Wait, what did you say it was?
Go again. Reset your mind. Get it to what it's supposed to be here. Rewrite this as an exponent.
Do we just save it? Yeah, we just save the. That's all.
Maria, what do you have?
I'm not sure.
You're not sure. Janae, what do you have?
3 to the power of x equals 1.7.
So we still have a few people out here on the sidelines that are marginalized by this. It's always the same thing. This is the base. The base of the log will always be the base of your exponent. Cody, it's not that hard. You're going to translate this stuff. Base for base. I need you to remember that logs are nothing more than exponents. Logs always equal the exponent. That x represents the exponent that you raise 3 to give you your antilog. This translation is consistently the same every time. I might change numbers, but we don't translate it any differently.
Just out of curiosity, but on the test, are you gonna expect from us to figure out what x is?
Yes, we're going to work on that even more today. In that problem, it would have been a negative 3.
What was that one again?
They were both been negative.
Which class got to use a calculator?
You should have been a Doyle's class.
I should have. Whose class? I knew I had Dolly. I don't know.
That's very true. that how you do it? See, but I don't understand what the point is.
We have to find that.
This should be 6 to the x equals 216. That's all I'm asking you to do right now. If you ended up figuring out that that ended up being a 3, fantastic. Next skill. All I want you to do is translate. If this is an exponential format, how do I get the logarithm format? Convert it. Maddie, you look confident. What did you put?
Log of 3 and
Now let's work on, that's exactly right. Let's work on reading these. This is a log of base 3 of 81 is 4. Now the whole purpose for logarithms is that they help us find exponents. Logs will always tell us the exponent. And yes, we're going to end up using a calculator to find those exponents. But we've got to have a system in place to go find them. Rewrite this using logarithms. Mr. Allenbach, what did you have there?
Log, base of 2, 32 equals 5.
Nice. Okay, somebody's saying, why do we need to do this? What are we doing this for? The first stage in learning how to use logarithms, you got to get comfortable with the language. This is the language I'm asking you. You got to know how to go from one stage or one format to another. Because sometimes we're trying to find the anti-log, and other times we're trying to find the exponent. It matters what form we write it in there.
Are there going to be any problems like these on the test, or is it just practice for?
This is part of your assessment.
This section.
Nate, what'd you put down for this?
That one?
Yep.
This was us, Rainbow Trees.
Couldn't hear you?
Well, you have log of log of base 2 times log of
Isn't it? You've got to be careful. It's not times. Okay, now that's twice I've heard it. I'm just trying to debunk this. This is the log of base 2 of 1/8 equals -3. It's really saying the same thing as this. It is an argument, just like taking the sine of a 90-degree angle is 1.
like take the log of
It's, yeah, the mathematical term is it's an argument. Okay, so I'm going to come back to this page, yeah.
some of the ones that we just did. Are you gonna on the test? Is there gonna be some where it's like 2 to the exponent of x equals 1/8, and you have to define what x is?
Yes,
Opposite.
yes, you'll have to know.
Okay.
So here's what we've worked with. That f at x equals a times b to the x. What kind of equation is this? It was called an exponential function. We looked at several examples yesterday of what we're going to have to do with these. We start off with 500 milligrams of medication in our bloodstream, and our body metabolizes 15%, so only 85% is left. After how much time will we be down to a certain amount of medication? We're going to be looking at exponential functions. But the problem with these exponential functions is we are not going to know what that exponent is. They're going to ask us to find the exponent. Now typically when we do exponents, here's what I want to make a point of. If I give you 2 to the x equals y, this thing is built for finding you the anti-log. The input value I'm going to put in here is going to be an exponent. So if I go 2 to the third, you're supposed to give me back out its output, its antilog, which is 8. Then we say, well, what if x is a 0? Well, 2 to the 0 is a 1. Exponential functions are built for finding the antilog. Now, part of your assessment is going to be on inverse functions. A logarithm is the inverse of an exponent. So if I ask you, what will the inverse function find? Well, if this thing is built for finding the antilog, we feed it an exponent, it gives us back an antilog, then what must its inverse function be built to accept? Antilog, so it can feed you back out the exponent. So when we finally get to these logarithm equations, we need the logarithm to help us find the exponent. It reverses the question. Rather than feed it an exponent, give me an antilog, feed it an antilog, it'll tell you your exponent. Now this seems pretty unnatural right now, but it's as natural as adding, subtracting, multiplying, dividing, squaring, and square rooting, whatever comparison you want to make to inverses that you've already studied. What makes it a little bit awkward right now is it's new. It's a long word. We've got to learn some translation. We've got to learn some language. Okay? So that's what we've been working on the last couple of days. Today we're going to push and try to figure out some common sense things. So here is an exercise of trying to figure out what should this exponent be between. So in question number 2 it says, without using the calculator, computer, log function, find the consecutive integers just below and just above the exact values of these logarithms. So let me make sure we understand what this is asking you for. This is a log of what base? 10 of 25. Really what this expression is supposed to go find is supposed to go find an exponent. Or in other words, we're supposed to find the exponent I raised 10 to get 25. That's my translation. That's the component I want to be able to flow back and forth in between. This means the same thing as this. But these are built for finding the exponent. Now right now, we've got to figure out what's it between. So here's what I'm going to start thinking of. Well, what is 10 to the first power? 10. Well, that's not big enough. What is 10 to the second power? 100. Well, that 25 is sandwiched in between there, so I know that my exponent that I'm going to go find better be between what?
1 and 2.
So this exponent is somewhere between a 1 and a 2. That's all we have to find for this right now. Making some common sense of these exponents. This one, the log of 314. It's really saying, what is the exponent I raised 10 to get 314?
Between 2 and 3.
So 10 to some power is 314. It's what's it between now?
2 and 3.
Okay, so you just rationalize it had to be between a 2 and a 3 because 10 to the third is equal to 1,000. And the number that they gave us, this 314, is in between there. So this exponent must be between a 2 and a 3. Now how about C? It's a 3.14. This is screaming. Find the exponent. You raise 10 to get 3.14, but what's it between?
0.
All right, so now we've got to go 10 to the 0. 10 to the 0 is 1. The 3.14 they gave us is somewhere between a 10 and a 1, so it must be between 0 and 1. We're going to stop at that. You get what they're asking you to do there? Reason between two integers what it has to be between. You're just saying make sure you can have at least some common sense in this and have an idea of what a realistic answer will be. The next stage is solving these equations. Now if you look at every single one of these equations, I want you to quickly examine them all. And I want you to tell me what is the base for every single one of these exponents. They're all base 10. Since they're all base 10, they have something really unique and in common. So let's try some of these. This one, we shouldn't even need to pick up the calculator. We ought to probably have it done. What do we raise 10 to get 100? 2. This one, almost as easy, but they got a 10 to the x plus 2 equals 100. X has to be a 0 because 0 plus 2 is 2 and 10 squared is 100. There's not a lot of reason for technology or anything on these. I want to jump down to some of these, probably down here at E. We can make some big jumps because there's a lot of correlation between base 10 and all bases. So we're going to go 2 times 10 to the x equals 600. Now this is all about PEMDAS. When we started the year, we started with getting rid of addition subtraction. I mean, in multiplication that we're going to finish the year with getting rid of exponents. We always work backwards. Is there any addition subtraction for us to get rid of? No. So then we work ourselves a little bit farther. Is there any multiplication division that I could get rid of?
Yes.
Yes. There's that multiplying by 2, and what would undo it?
Divide by 2.
You'll divide by the 2. So 10 to the x equals 300. Now look at where your variable is. Where is our variable located? I understand what you just answered for me. Okay, where is our variable in this equation? It is in the exponent. That's what I want to proclaim here. That's the part that's important. If it's in the exponent, how do we undo exponents? And I've given you some keys to this thing. What is the inverse of an exponent? A logarithm. Now, in order to be successful with this, we want to convert this into a log statement. It's a log of what base? Base 10 of 300 will give you your exponent. See, that's what logs are intended to do. Logs are intended to inform you what that exponent has to be. Now, you've already reasoned it's got to be between 2 and 3. Well, it just so happens our calculators have a log function on them. Log, there's your LOG key. This LOG key is only good for log base 10. You understand that? Not a log base 2, not a log base 3. It's only good for log base 10. Do I have a log base 10 there? So I hit my log key. It says the common log. That's the name for base 10. We want to take the common log of 300. Close your parenthesis to be official. You hit enter. What is that answer supposed to be? Okay, I know the number. What is it supposed to represent? The exponent. You raise what to? 10 to get what value? All right. So here's what I'm going to check. I'm going to go second. Look behind your log key. What do you see? 10 to the x. If I raise 10 to this power I just found, it better give me. So I'm going to go second, answer, 300. Now we're going to have to round our answers. Bottom line is we're just going to have to round it. We're going to round to the nearest hundred. So if we round this to the nearest hundred, it's 2.4. So what happens if I were to take 10 and raise it to the 2.48? Did I round up or down?
So
If I round it up, it's going to be bigger than 300 or smaller than 300? And that's just what we're going to have to do, because we're not going to be able to write all those decimal places down. You understand? Logarithms are here to help us find exponents. We won't get nice, neat, short answers. We're going to have to round them. But it's a log base 10. So let's try another one. Let's go to G. We've got 10 to the 3x plus 1 equals 43. Let's work through our PEMDAS. That's our system in place. Do we have any addition, subtraction we need to get rid of?
Yes.
No.
Officially, yes, we do. But where is it? Since it's in the exponent, it's locked up in there in this exponent concept. So we can't get rid of any addition, subtraction right away. Is there any multiplication, division? No, there's not. So where are we already?
exponent.
So what are we going to do to undo exponents?
Log.
That's why I've taught you the last day and today how we change it from an exponential format to a log format. It's got to be a log of what base? 10, which is called your common log. We take the common log of what value? 43, and that will allow us to figure out what is in that exponent. Now it's nice, we've improved it, but we still want to get x by itself, so what other things must we do? Okay, now we come back to PEMDAS again. We've got some addition to get rid of, so let's get rid of it. We'll take the common log of 43, we'll subtract 1. What else do we have to do? Finally, we have to divide by 3. So when we find that value, it's going to be the log of 43 minus 1, then divided by 3. Now you got to be somewhat careful when you put this in your calculator. You might want to take it in small steps. I'm not sure the best answer for you on that. But if you want to take it in small steps, the first thing we did is we said take the log of 43. Okay, there it is. What were we supposed to do with this answer?
Minus 1.
Then you subtract 1. After you subtracted 1, what were we supposed to do? Divide by 3. There's your exponent. If I take this times 3, add 1, and raise 10 to that power. What should I get? 43. Okay, so that says if I take 10 to the power of, give me a 10, 3 times my answer I just got, then I have to add 1. It better give me Yahtzee. Logarithms help us find the exponent. This button right here, when you hit that, is going to give you a what? Because logarithms find exponents. They're your inverses. Okay, we're going to do one more of these, and then we got to jump to another idea here. Let's try I. Letter I. Lots of things in here. We got 5 times 10 to the x plus 3 plus 9 equals 44. PEMDAS backwards. What is it telling us we need to get rid of first? Adding that 9. And to undo that, we will subtract it. So if we subtract 9 from 44, we're left with a 35. Okay, now what do we need to do?
Divide by 5.
Yeah, now the multiplication takes precedence, so we'll divide by 5. So 10 to the x minus 3 equals a 7. Now we're at what level in PEMDAS? In the exponents. So now, in order to get that out of there, we have to use logarithms. It must be a log of base 10. Plus 3? Okay, thank you. Log of base 10 of 7 must equal x plus 3. In order to find x, what do we need to do? Subtractor 3. So it's the common log of 7 minus 3. You don't have to put the 10 down there if it's just a common log. Be careful that you close the parentheses one more time. I want to emphasize, as soon as you hit that log key, notice it puts in a parenthesis. That's your argument. We have to take the log of 7, common log, close it, and we can subtract our 3. Negative 2.15. It'll be our approximate answer. Okay, number 4. We're probably going to have time to do 2 out of 3. So we'll go through, we'll just take them in order, A and B. And then we'll skip C, just because once you get the idea of one of them, the rest of them are pretty much the same. What we're going to do is we're going to take those things we talked about yesterday in the opening part of our lesson, and we're going to solve them. Yesterday we said we had a bacteria dish in the lab dish. And at any time, T hours after the start of the experiment, we could figure out the number of bacteria based on this equation. The number of bacteria at any given time was 50 times 10 to the 0.3 T. Now this 50 stood for the what?
Is the starting amount.
The starting amount. We start off with 50 bacteria. This thing in here is your rate of growth. If you would, someone to do this, take 10 to the 0.3 power. What is that?
1.9953.
Right. Now yesterday, when we read that, it said every hour we expect the bacteria to double its size. This 10 to the 0.3 is nothing more than 2. You with me? They already changed it to base 10, raised to the T. We want to know when the population will be 10,000 bacteria. Now this 10,000 represents a population, or the total number of bacteria at a given time. We got to put that 10,000 in there. Put 10,000 in for that. We started with 50. Our growth rate was 10 raised to 0.3, and it doubles basically every hour. Solve this. So the first thing we do is divide by your 50. If you divide by your 50, you're left with 200. Equals 10 to the 0.3 T. Now, only thing that we're left with are things left in the, which means we have to dip in and use our new inverse. Logarithm of base 10, or common logarithm of 200 has to be your exponent 0.3 T. that means our time has to be whatever the log of 200 divided by 3/10 is. 7.7 hours, basically. In about 7.7 hours, we can take 50 bacteria, have them multiplied to a population of 10,000 in virtually 7.7 hours. That's why we need to have logarithms. There are certain problems that we need to find the exponent. And then we'll do the baseball one, and then we'll move on to other bases. This is about the Washington Nationals baseball team. Yesterday they said, when we read it, in 2006, that person paid $450 million for it, individual or a corporation. We wanted to know how long it would take before it was worth $1 billion. Now just, you remember how many millions there were in a billion? Yeah, imagine having 1,000 stacks of a million to finally get to a billion. We want our 450 million to reach 100,000 million dollars. If we had a growth rate, and this 10 to the 0.02 t, that's your 5% growth rate, which they said is pretty modest. So, in order to solve, we have to do what?
Divide by 450.
Divide by 450. Now that's a little problematic. When you do that, do you get a nice clean number?
No.
So just leave it as 1,000 divided by 450. If you get a nice neat number that stops, great. If it doesn't, I just leave it that way.
Can you take that out? Can you simplify it?
You may. You can take that off if you want to reduce it. You can divide them both by 5, so it's 20 over 9. Doesn't matter. It's all the same. Equals 10 to the 0.02 t. Well, that's equal to 10 to the 0.02 t. We reduced this fraction to get 29. That's all. You don't have to. Your calculator will handle it just fine if you don't. What do we have to apply?
You have to do the log,
Now you got to do the log. I'm going to use 29 just because it's a smaller number.
and then
Equals 0.02 t.
then you divide it by
Divided by 0.02. Word of caution on this one. If you're going to do that, make sure that you get this all wrapped up in your log. It's the log of 20 divided by 9. Oops, get my divided by sign in there. Pretty sure that's it. There we go. Then close your parentheses. That's what we want. Then divide it by 0.02. This should happen in about, wow. Now I didn't get my division sign. All right, come on. 0.2. That looks better. In about 17.3 years, 17 years and a third and 4 months, we can take $450 million and make it worth $1 billion. Okay? Every single one of these has been a base what? 10. Here's the change. Not everything is base 10. If you look at investigation 2, it says covering all the bases. So there's one last thing I'm going to teach you this year. This is the last thing. This is the last new thing I got all year. We got to be able to change with the bases. So we're going to be trying to find the exponent I raised 2 to get 3.5. That's really what we're after. What is that exponent that I raised 2 to get 3.5? Well, I know it's somewhere between 2 and 1. 2 to the first is 2. 2 to the second is 4. So I know it's somewhere in between here. Probably a little closer to 2 than it is to 1. So again, I'm going to try to solve this. Well, PEMDAS backwards says I must get this exponent out of there. And what's the inverse of exponents?
log.
Logarithms. Let's change it to a log statement. It's got to be a log of what base? Log of base 2
Times 3.
of
3.5
3.5 has to equal
x.
x. This logarithm statement is trying to help you find that exponent. Unfortunately, our calculator doesn't have a base 2. Calculators are basically have two bases. This log is base 10. This ln is base e. And that's really weird. E is like pi. You know what pi is like? 3.14159 goes on forever. Same thing with E. E is 2.7, 1828, 1828 goes on forever as well. We're not going to mess with base E this year, just base 10. Here's your final piece. If we run into a different base, you will have to use something called the change of base formula. It's really quite easy. That's why most of these engineers at TI or whoever makes your calculator don't put on a bunch of buttons for a lot of different bases. What we do is we take the common log of 3.5 divided by the common log of 2. This takes care of it. Rather than using a base 2 logarithm, which we don't have, we take the log of the top thing divided by the log of the bottom thing, and we use common log. This is not magic, I'm telling you, it's not magic, it's just math. We're going to do the log of 3.5, then we're going to divide it by the log of 2. Still didn't get, what's wrong with my division deal? What is that thing supposed to be? That's supposed to be that exponent. Supposedly, if I take 2 and I raise it to that power, the whole power, what should it give me? You go back. Yahtzee. You got it? It's called a change of base formula. It's the only thing you need to do to get to other bases, to cover your bases. Let's do 2 of these. Let's do letter C, and let's come back and do F. C. PEMDAS backwards. What's it going to force you to concentrate on first? Subtracting the 20, so it's going to be 5 times 2 to the t equals 105. Now what does PEMDAS force you to do? Divide by 5, so that means 2 to the t equals 21. We are now back to our exponent. So we're going to use logs. It's better be a log of what base? Base 2 of
21
equals t. Since we don't have a log base 2 button, what do we use? Common log of 21 divided by the common log of 2. But I want you to tell me what you just utilized. What did I say that was?
Change of base formula.
Change of base formula. Link it in your head. It's a change of base formula. Run your computation and you're there. 4.48.
4.39.
All right, round it, be done. That's not my focus, is rounding. So let's do letter F. The only reason I want to do letter F, I want to show you that even quirky bases work. It's 300 times 0.9 to the v equals 60. What does PEMDAS immediately say you got to get rid of? The 300, so it's 0.9 to the v equals 60 divided by 300. That's a really nice number. I'm going to reduce it. That's 6 over 30, which is 1 over 5, and 1 over 5 is 0.2. You can use your 60 over 300, it won't hurt a thing. What do we have to do to find v? Log of what base? 0.9 of 0.2 is v. See, these bases can be whatever we need them to be. Now we're going to have to use our, what's the name of it? Change of base. Take the common log of 2/10 divided by the common log of 9/10. 15.28? All right. That's all I got to teach you, but we're going to apply it in some other settings. We might get 2 of these done. We'll see. In question 4, we have to build the equation, then we have to solve it. So question 4, we build an exponential equation, and if we're going to build it, folks, we've got a basic building block here. Y equals a times b to the x. This is what every exponential function is built from. I don't recall. No, this is still part of investigation. It says, I gotta get going here, Tony, okay? If the world population at the beginning of 2008 was 6.7 billion and growing exponentially at a rate of 1.16% per year, what year will the population double? We've got to build it first. Whenever we build an exponential equation, this A is always going to be your starting point. This B is going to be your rate of growth, or sometimes it will be decay. This one has to be growth. Now, because it's population, I'm going to say the population at any given time. What kind of notation am I using? Function notation. I can find the population if you feed me a time. That's what it's saying. What was our start at population? 6.7 billion. Now we got to get our rate of growth in here correctly. It was a rate of increase of 1.16%. We never use percents in our math. What do we change them to? Bump, bump. 0.0116. Now that's a rate of growth. If it's going to grow, it's got to be a number bigger than what? Talked about yesterday. It will not grow unless our rate of growth is bigger than what? 1. So it's 1.0116. It's your current population plus your growth. So 1.0116 to the t. Still trying to build our equation. What do we want our population to be? Double. So what do I want this population to end up being? 13.4. We just doubled this. If 13.4 is double, how long will it take? If we continue on a growth rate of 16 or 1.16%, how many years will it take for our population double? Divide by 6.7. That gives us a nice neat 2. It better be a 2. We just said it was going to double there. What do we need to use? Logarithm. It's going to be a logarithm of what base? Of equals t. We have to elicit the use of a change of base formula. Is your time. If you run the calculation, you should get right at 60 years. So if this is about 60 years, then it's going to be 2068 when we hit that double our population. Now, I don't think we're going to have time to solve it, but I want to set up one more. Because setting them up sometimes is the hardest part at this point. We're going to do B. Oh, what the heck, let's do C. Kalamazoo. Who can pass up Kalamazoo? The average rent for a 2-bedroom apartment in Kalamazoo, Michigan is currently $750 a month and increasing at a rate of 8% per year. And how many years will the average rent for such apartments reach 1,000? What's our start at value? 750. What was our rate of growth? So it's 1.08 to the t, and this is our rent at any given time. But what do we want our rent to end up being? There's our equation. Now we still have to run through PEMDAS backwards. We still have to use our logarithms. We still have to use our change of base formula. But we can calculate this. Folks, I need you to finish. The finish line is really, really close. I know you can see it. I can see it too. I can smell it. We're 2 days away. Finish. I need this assignment done. There's a lot here. It's going to be turned in Tuesday. I want to see who's finishing for me. Make it to the tape. Get the assignment done. Get it turned in so I can look at it. Tuesday, Wednesday are probably days reserved for assessment on inverse functions and logarithms. Solving equations with logarithms. Don't let up. Finish it. Get there. You will turn in both of these. See those that I have circled? We're going to do that and all of that.
Okay.
Because yesterday I gave the CYU and the number 1. After today's discussion, we ought to have a better sense of how to do everything.